Three-phase electric power is a common method of alternating current electric power generation, transmission, and distribution. It is a type of polyphase system and is the most common method used by electrical grids worldwide to transfer power. It is also used to power large motors and other heavy loads. A three-phase system is usually more economical than an equivalent single-phase or two-phase system at the same voltage because it uses less conductor material to transmit electrical power. The three-phase system was independently invented by Galileo Ferraris, Mikhail Dolivo-Dobrovolsky and Nikola Tesla in the late 1880s. Details. In a three-phase power supply system, three conductors each carry an alternating current, but the phase of the voltage on each conductor is displaced from each of the other conductors by 120 degrees. Hence, the voltage on any conductor reaches its peak at 1/3 of a cycle after one of the other conductors and 1/3 of a cycle before the third conductor. Using the voltage on one conductor as the reference, the peak voltage on the other two conductors is delayed by 1/3 and 2/3 of one cycle respectively. This phase delay gives constant power transfer over each cycle. It also makes it possible to produce a rotating magnetic field in an electric motor. With a three-phase supply, at any instant, the potential of any phase is exactly equal to and the opposite of the combination of the other two phases. This means that, if the load on the three phases is balanced, the return path for the current in any phase conductor is the other two phase conductors. Hence, the sum of the currents in the three conductors is always zero and the current in each conductor is equal to and in the opposite direction as the sum of the currents in the other two. Thus, each conductor acts as the return path for the currents from the other two. While a single-phase AC power supply requires two conductors, a three-phase supply can transmit 3 times the power by using only one extra conductor. This means that a 50% increase in transmission cost yields a 200% increase in the power transmitted. Three-phase systems may also utilize a fourth wire, particularly in low-voltage distribution. This is the neutral wire. The neutral allows 3 separate single-phase supplies to be provided at a constant voltage and is commonly used for supplying groups of domestic properties which are each single-phase loads. The connections are arranged so that, as far as possible in each group, equal power is drawn from each phase. Further up the supply chain in high-voltage distribution, the currents are usually well balanced and it is therefore normal to omit the neutral conductor. Three-phase supplies have properties that make them very desirable in electric power distribution systems. The phase currents tend to cancel out one another, summing to zero in the case of a linear balanced load. This makes it possible to reduce the size of the neutral conductor because it carries little to no current. All the phase conductors carry the same current and so can be the same size, for a balanced load. Power transfer into a linear balanced load is constant, which helps to reduce generator and motor vibrations. Three-phase systems can produce a rotating magnetic field with a specified direction and constant magnitude, which simplifies the design of electric motors. Most household loads are single-phase. In North American residences, three-phase power might feed a multiple-unit apartment block, but the household loads are connected only as single-phase. In lower-density areas, only a single phase might be used for distribution. Some large European appliances may be powered by three-phase power, such as electric stoves and clothes dryers. Wiring for the three phases is typically identified by color codes which vary by country. Connection of the phases in the right order is required to ensure the intended direction of rotation of three-phase motors. For example, pumps and fans may not work in reverse. Maintaining the identity of phases is required if there is any possibility two sources can be connected at the same time. A direct interconnection between two different phases is a short circuit. Generation and distribution. At the power station, an electrical generator converts mechanical power into a set of 3 AC electric currents, one from each coil of the generator. The windings are arranged such that the currents vary sinusoidally at the same frequency but with the peaks and troughs of their waveforms offset to provide 3 complementary currents with a phase separation of 1/3 cycle. The generator frequency is typically 50 or 60 Hz, varying by country. At the power station, transformers change the voltage from generators to a level suitable for transmission, minimizing losses. After further voltage conversions in the transmission network, the voltage is finally transformed to the standard utilization before power is supplied to customers. Most automotive alternators generate three-phase AC and rectify it to DC with the diode bridge. Transformer connections. A delta-connected transformer winding is connected between phases of a three-phase system. A Y-transformer connects each winding from a phase wire to a common neutral point. In an open delta, or V system, only two sets of transformers are used. A closed delta system can operate as an open delta if one of the transformers has failed or needs to be removed. In open delta, each transformer must carry current for its respective phases as well as current for the third phase, therefore capacity is reduced to 87%. With one of three transformers missing and the remaining two at 87% efficiency, the capacity is 58% or 87%. Where a delta-fed system must be grounded for protection from surge voltages, a grounding transformer may be connected to allow ground fault currents to return from any phase to ground. Another variation is a corner-grounded delta system, which is a closed delta that is grounded at one of the junctions of transformers. 3-wire and 4-wire circuits. There are two basic three-phase configurations, delta and Y. As shown on the left, a delta configuration requires only 3 wires for transmission, but a Y configuration may utilize a fourth wire. The fourth wire, if present, is provided as a neutral and is normally grounded. The 3-wire and 4-wire designations do not count the ground wire used above many transmission lines, which is solely for fault protection and does not carry current under non-fault conditions. A 4-wire system with symmetrical voltages between phase and neutral is obtained when the neutral is connected to the common star point of all supply windings. In such a system, all three phases will have the same magnitude of voltage relative to the neutral. Other non-symmetrical systems have been used. The 4-wire Y system is used when ground referenced voltages or the flexibility of more voltage selections are required. Faults on one phase to ground will cause a protection event locally and not involve other phases or other connected equipment. An example of application is a local distribution in Europe, where each customer is fed from one phase and the neutral. When a group of customers sharing the neutral draw unequal currents, the common neutral wire carries the currents resulting from these imbalances. Electrical engineers try to design the system so the loads are balanced as much as possible. By distributing a large number of houses over all three phases, on average a nearly balanced load is seen at the point of supply. In North America, a high-leg delta supply is sometimes used, where one winding of a delta-connected transformer feeding the load is center-tapped and that center-tap is grounded and connected as a neutral, as shown on the right. This setup produces three different voltages. If the voltage between the center-tap and each of the two adjacent phases is 120 V, the voltage across any two phases is 240 V and the neutral to high-leg voltage is a per-mil 208 V. The reason for providing the delta-connected supply is usually to power large motors requiring a rotating field. However, the premises concerned will also require the normal North American 120 V supplies, two of which are derived between the neutral and either of the center-tap phase points. Balanced circuits. In the perfectly balanced case, all three lines share equivalent loads. Examining the circuits, we can derive relationships between line voltage and current, and load voltage and current for Y and delta connected loads. In a balanced system, each line will produce equal voltage magnitudes at phase angles equally spaced from each other. With V1 as our reference and V3 lagging V2 lagging V1, using angle notation, we have these voltages feed into either a Y or delta connected load. Y. For the Y case, all loads see their respective line voltages, and so, where Z-total is the sum of line and load impedances, and I is the phase of the total impedance. The phase angle difference between voltage and current of each phase is not necessarily zero and is dependent on the type of load impedance, ZY. Inductive and capacitive loads will cause current to either lag or lead the voltage. However, the relative phase angle between each pair of lines will still be a 120 degrees. By performing Kirchhoff's current law on the neutral node, the three-phase currents sum up to the total current in the neutral line. In the balanced case, delta. In the delta circuit, loads are connected across the lines and so loads see line-to-line voltages. Further, whereas the phase of delta impedance, relative angles are preserved, so I31 lags I23 lags I12 by 120 degrees. Calculating line currents by using KCL at each delta node gives AAAAA, and similarly for each other line. Again, I is the phase of delta impedance. Single-phase loads may be connected across any two phases, or a load can be connected from phase to neutral. Distributing single-phase loads among the phases of a three-phase system balances the load and makes most economical use of conductors and transformers. In a symmetrical three-phase four-wire, Y system, the three-phase conductors have the same voltage to the system neutral. The voltage between line conductors is ℏ3 times the phase conductor to neutral voltage. VLL equals ℏ3 VLN. The currents returning from the customer's premises to the supply transformer all share the neutral wire. If the loads are evenly distributed on all three phases, the sum of the returning currents in the neutral wire is approximately zero. Any unbalanced phase loading on the secondary side of the transformer will use the transformer capacity inefficiently. If the supply neutral is broken, phase to neutral voltage is no longer maintained. Phases with higher relative loading will experience reduced voltage and phases with lower relative loading will experience elevated voltage, up to the phase-to-phase voltage. A high lag delta provides phase-to-neutral relationship of VLL equals to a VL however, Ln load is imposed on one phase. A transformer manufacturer's page suggests that Ln loading to not exceed 5% of transformer capacity. ℏ3 is a per mil 1.73, so if VLN was defined as 100%, VLL would be a per mil 100%. 1.73 equals 173%. If VLL was set as 100%, then VLN a per mil 57.7%. Unbalanced loads, when the currents on the three live wires of a three-phase system are not equal or are not at an exact 120-degree phase angle, the power loss is greater than for a perfectly balanced system. The method of symmetrical components is used to analyze unbalanced systems. Nonlinear loads. With linear loads, the neutral only carries the current due to imbalance between the phases. Devices that utilize rectifier capacitor front ends such as switch-mode power supplies, computers, office equipment and such produce third-order harmonics that are in phase on all the supply phases. Consequently, such harmonic currents add in the neutral which can cause the neutral current to exceed the phase current. Three-phase loads. An important class of three-phase load is the electric motor. A three-phase induction motor has a simple design, inherently high starting torque and high efficiency. Such motors are applied in industry for many applications. A three-phase motor is more compact and less costly than a single-phase motor of the same voltage class and rating, and single-phase AC motors above 10 horsepower are uncommon. Three-phase motors also vibrate less and hence last longer than single-phase motors of the same power used under the same conditions. Line frequency flicker in light can be reduced by evenly spreading three phases across line frequency-operated light sources so that illuminated area is provided light from all three phases. The effect of line frequency flicker is detrimental to super slow-motion cameras used in sports event broadcasting. Three-phase lighting has been applied successfully at the 2008 Beijing Olympics to provide consistent light level for each frame for SSM cameras. Resistance heating loads such as electric boilers or space heating may be connected to three-phase systems. Electric lighting may also be similarly connected. Rectifiers may use a three-phase source to produce a 6-pulse DC output. The output of such rectifiers is much smoother than rectified single-phase and, unlike single-phase, does not drop to zero between pulses. Such rectifiers may be used for battery charging, electrolysis processes such as aluminium production or for operation of DC motors. Zigzag transformers may make the equivalent of 6-phase full-wave rectification, 12 pulses per cycle, and this method is occasionally employed to reduce the cost of the filtering components, while improving the quality of the resulting DC. One example of a 3-phase load is the electric arc furnace used in steelmaking and in refining of ores. In Germany, a 1965 publication shows some full-size stoves are designed for a 3-phase feed. However, the individual heating units may be connected between phase and neutral to allow for connection by 3 individual circuits on the same single-phase supply. Phase converters are used when 3-phase equipment needs to be operated on a single-phase power source. They are used when 3-phase power is not available or cost is not justifiable. Such converters may also allow the frequency to be varied, allowing speed control. Some railway locomotives use a single-phase source to drive 3-phase motors fed through an electronic drive. Mechanical. One method to generate 3-phase power from a single-phase source is the rotary phase converter, essentially a 3-phase motor with special starting arrangements and power factor correction that produces balanced 3-phase voltages. When properly designed, these rotary converters can allow satisfactory operation of a 3-phase motor on a single-phase source. In such a device, the energy storage is performed by the inertia of the rotating components. An external flywheel is sometimes found on one or both ends of the shaft. A 3-phase generator can be driven by a single-phase motor. This motor-generator combination can provide a frequency changer function as well as phase conversion, but requires 2 machines with all their expense and losses. The motor-generator method can also form an uninterruptible power supply when used in conjunction with a large flywheel and a standby generator set. Non-mechanical, a second method that was popular in the 1940s and 1950s was the transformer method. At that time, capacitors were more expensive than transformers, so an autotransformer was used to apply more power through fewer capacitors. Separated it from another common method, the static converter, as both methods have no moving parts, which separates them from the rotary converters. Another method often attempted is with a device referred to as a static phase converter. This method of running 3-phase equipment is commonly attempted with motor loads, though it only supplies 2/3 power and can cause the motor loads to run hot and in some cases overheat. This method does not work when sensitive circuitry is involved, such as CNC devices, or in induction and rectifier type loads. Variable frequency drives are used to provide precise speed and torque control of 3-phase motors. Some models can be powered by a single-phase supply. VFDs work by converting the supply voltage to DC and then converting the DC to a suitable 3-phase source for the motor. Digital phase converters are designed for fixed frequency operation from a single-phase source. Similar to a variable frequency drive, they use a microprocessor to control solid-state power switching components to maintain balanced 3-phase voltages. Alternatives to 3-phase, split-phase electric power is used when 3-phase power is not available and allows double the normal utilization voltage to be supplied for high-power loads. 2-phase electric power, like 3-phase, gives constant power transfer to a linear load. For loads that connect each phase to neutral, assuming the load is the same power draw, the 2-wire system has a neutral current that is greater than neutral current in a 3-phase system. Also, motors are not entirely linear, which means that despite the theory, motors running on 3-phase tend to run smoother than those on 2-phase. The generators in the Adams power plant at Niagara Falls that were installed in 1895 were the largest generators in the world at the time and were 2-phase machines. True 2-phase power distribution is obsolete for new work applications, but still exists for old work applications, perhaps most particularly in Buffalo and Niagara Falls, New York, Toronto and Niagara Falls, Ontario, Philadelphia and Reading, Pennsylvania, and Camden, New Jersey. New work 3-phase installations may be supplied by old 2-phase feeders, and old work 2-phase installations may be supplied by new 3-phase feeders using a Scott T transformer, invented by Charles F. Scott. Special purpose systems may use a 2-phase system for frequency control. Monocyclic power was a name for an asymmetrical modified two-phase power system used by General Electric around 1897, championed by Charles Proteus Steinmetz and L. Thompson. This system was devised to avoid patent infringement. In this system, a generator was wound with a full-voltage single-phase winding intended for lighting loads and with a small fraction winding that produced a voltage in quadrature with the main windings. The intention was to use this power wire additional winding to provide starting torque for induction motors, with the main winding providing power for lighting loads. After the expiration of the Westinghouse patents on symmetrical two-phase and three-phase power distribution systems, the monocyclic system fell out of use. It was difficult to analyze and did not last long enough for satisfactory energy metering to be developed. High-phase order systems for power transmission have been built and tested. Such transmission lines typically would use 6 phases or 12 phases. High-phase order transmission lines allow transfer of slightly less than proportionately higher power through a given volume without the expense of a high-voltage direct current converter at each end of the line. However, they require correspondingly more pieces of equipment. Color codes. Conductors of a three-phase system are usually identified by a color code, to allow for balanced loading and to assure the correct phase rotation for induction motors. Colors used may adhere to International Standard IEC 60446, older standards or to no standard at all and may vary even within a single installation. For example, in the US and Canada, different color codes are used for grounded and ungrounded systems. See also, three-phase AC railway electrification, charging station, frequency converter, industrial and multiphase power plugs and sockets, International Electrotechnical Exhibition, John Hopkinson, Why I Transform, Notes. References